Hello again. In this video, we're going to talk about how we find local maxima and local minima using what is known as the first derivative test. Okay, so here's what the first derivative test says. Assume that f is continuous on an interval that contains a critical point c, and assume f is differentiable on an interval containing c, except perhaps at c itself. Now, if f prime changes sign from positive to negative as x increases through c, then f has a local maximum at c. But if the derivative changes sign from negative to positive as x increases through c, then f has a local minimum at c. And if the derivative does not change sign at c, then f prime has no local extreme value at c. Okay, so let me show you why the first derivative test allows us to find the location of local maximums and local minimums. So let's say we have a function whose graph looks like this. Now notice there are several locations where we have critical points. Now remember, a critical point is where the derivative is either 0 or is undefined. And so you can see there are several places where we have critical points. We have one at these locations because the derivative is 0. And then we also have one right here because the derivative doesn't exist at that point because it's a sharp corner. So we actually have 1, 2, 3, 4, 5 critical points. Now notice that at some of these critical points we have local maxima or maximums. Like right here we have a local maximum. And at other places we have local minimums. And here's a local maximum. At these two spots, we have neither a local maximum or a local minimum. So, just because you have a critical point doesn't mean you have a local maximum or a local minimum. It could be neither, because these particular situations can occur. So when we run the first derivative test, the first thing we're going to do is find all the critical points for the function. And then we're going to classify those critical points as being either being the location of a local maximum, the location of a local minimum, or neither, because it's going to be one of the three. So we find the critical points first, and then we classify them. Now, how are we going to classify them? How are we going to know if they're the location, if these critical points are the location of a local maximum or a local minimum or neither? Well, here's how we're going to tell. Notice here that we have neither a local max or local min at this critical point. And notice on the left-hand side of this critical point, the function's increasing. In other words, the derivative is positive over here. But it's also increasing on the right-hand side. And again, the derivative is positive because it's increasing. So it's not changing sign, right? The derivative is not changing sign at this as it passes through this critical point. And so the first derivative test says that we have neither a local max nor a local min when that happens. Now, it could also be the case that the function, let's take this critical point here, right? It could also be the case that the function's decreasing on the left of the critical point, but then also decreasing on the right of the critical point. And then in that case, it's not changing sign, all right? The derivative is not changing sign across the critical point, and therefore you don't have a local max or local min at that critical point. Now let's look at this critical point. Notice here that the function's increasing to the left of the critical point, and it's decreasing to the right. In other words, the derivative is positive on the left and then negative on the right. So if that happens, then when you increase and then decrease at that critical point as you pass through it, then that means you have a local maximum there. Whereas if you have a local minimum, like at this critical point, then what's going to happen is to the left of that critical point, the derivative is going to be negative because it's decreasing. And then to the right of that critical point, the derivative is going to be positive because it's increasing. And that creates the local minimum. Okay, and so that's what the first derivative test is basically doing for us. We first find all the critical points, and then we go through and we classify them as being the location of a local max, a local min, or neither by looking at the sign of the derivative on the left side of the critical point and on the right side of the critical point. Okay, so let's do an example where we actually apply the first derivative test so you can see how this works. So let's look at example 3. So for this particular function, let's try to find the location of all its local maximums and all its local minimums. Okay, so the first thing we're going to do is when we use the first derivative test, we have to find all the critical points, and then we're going to try to classify them. Okay, so we need to find the critical points. Now remember, the critical points are when the derivative is equal to 0 or doesn't exist. Okay, so let's find the derivative. All right, so in this case, the derivative would be 12x cubed minus 12x squared minus 12x plus 12. Okay, now let's look at both cases where we can get critical numbers, when the derivative is 0 and then when it doesn't exist. Okay, let's start with doesn't exist. Okay, this is a third degree polynomial, right? The derivative is a third degree polynomial. And we know that polynomials exist for all numbers. And you can think about that, right? If you plug any number in for this x here, you're going to get a number out. So the derivative always exists, right, for any x value that you plug into it. And so this never happens. Okay, so we don't get any critical numbers here. And that's basically telling us that the function doesn't come to any of these sharp corners like this. Okay, now let's check and see when the derivative is 0. Okay, and of course here, let's go ahead and factor out the 12. And then if you really want to, it's probably a good idea just to divide both sides by 12. Just to get rid of this 12, and then you're just left with this third degree polynomial. Okay, now we want to know when this is equal to 0. So we probably need to factor this if we're going to have any hope of finding out when it's equal to 0. So one possibility is you could try to factor by grouping. Anytime you have 4 terms, you should think about the possibility that you could factor it by grouping. So if we look at these first 2 terms, the way we do factoring by grouping is we pair up 2 of the terms, and then we pair up the other 2 terms, and then we factor out what those pairs have in common. So these 2, if we pair them up, they have an x squared in common. And so I'm going to factor that out, and that's going to leave us with an x minus 1. Then these 2 don't have anything in common. I'm going to pull out a negative 1. Okay, and that's going to leave us with x minus 1. And if these 2 are the same, right, the stuff that's left in the parentheses, if they're the same, then you can factor that out from both of these terms, right? So look at this as 2 different terms. You have this term minus this term. They have something in common, right? They both have an x minus 1 in common. And so you can factor out that x minus 1, and that's going to leave you with x squared, right? When you pull x minus 1 out of here, you're left with x squared. And when you pull x minus 1 out of here, you're left with a minus 1. Okay, and so that's how this factors. And you can check this if you want. Go ahead and FOIL this out, and when you FOIL this out, you're going to get these 4 terms. Okay, and now we can factor this. That's the difference of squares, so we just get x plus 1 times x minus 1. Okay, and then if you go ahead and solve this, x minus 1 would have to be 0, or x plus 1 would have to be 0. And so we end up with two answers here. We get x equals 1, and we get x equals negative 1. Okay, now remember, in order for these to be critical points, they have to be in the domain of the function. And if you go look back at the original function, this is a polynomial, so its domain is all real numbers. And of course, these are both in there, in that interval. So these are critical points. Okay, so now, what we're going to do is we're going to take the number line and we're going to break it up at these critical points. So at negative 1 and 1. And then we're going to pick off the intervals that are created here. So one interval that's created is this one from negative infinity to negative 1. And then we have one from negative 1 to 1. And we also have one from 1 to infinity. Then what we're going to do is we're going to test to see whether the function's increasing or decreasing in each of these intervals by picking a test point and plugging it into the derivative from each of the intervals. So a good test point in here might be negative 2. So I'm going to take negative 2 and plug it into the derivative. Okay. Now when you plug negative 2 into the derivative, right, you have to plug negative 2 in here, negative 2 in here, and negative 2 in there. And so it looks like you're going to get negative 96 minus 48 plus 24 plus 12. Okay, and don't really need to worry about exactly what this number is, but this number is clearly a negative number. Okay, we'll go ahead and figure out what it is, but don't actually have to calculate whether it's what the specific number is. You just need to know whether it's negative or positive. In this case, this is going to be negative, but let's go ahead and figure out what it is. So you get negative 12 here when you add these together, and then minus 96 would be negative 108. Okay, but the important thing is that it's negative, and that indicates that the function is decreasing. Okay, so we know the function is decreasing in this interval. All right, so let's take a test point in here. Maybe 0 would work. And you plug that into this, the first derivative, and you get 12. Okay, and that means the function's increasing. Okay, and then I'll pick 2 for a test point in here. Okay, plug that into the derivative, and you're going to get, 2 cubed is 8. 8 times 12 is 96. And then here you get 2 squared is 4. 4 times negative 12 is negative 48. And then 2 times negative 12 is negative 24 plus 12. Okay, and so it looks like you get 108 minus 72, and that's equal to 36. Okay, so it's positive, and that means the function's increasing. Okay, so we've got 2 critical points, and we're going to try to classify them as the location of a local maximum, a local minimum, or neither. And let's start with negative 1. So looking at negative 1, right, which is right here, the function is decreasing to the left of it, and then the derivative is 0 right at negative 1, right, because that's the reason we set the derivative equal to 0, and we got negative 1 and 1, right? So the derivative is 0 at both of these spots. So we get a smooth transition from decreasing to increasing. Not an abrupt one, right? Because an abrupt one would have appeared under this case, and we didn't have any of those. So all of our transitions are smooth. Okay, so on this side, it's increasing, right? So we have a smooth transition from decreasing to increasing, which indicates that there's a local minimum right at x equals -1. Okay, so that's the location of a local minimum. Okay, now at 1, it's increasing to the left of it. And then at 0, right at 1. Again, that's because we know that the derivative evaluated at 1 is 0, because we got a 1 here under this case. And then on the right-hand side, it's decreasing. Sorry, it's increasing. So it's increasing, and it continues to increase. But apparently it levels off, right? It has to level off right in here in order for the derivative to be 0 at that particular point, at 1. Okay, so this is a location where you have neither a local max nor a local min. Now, notice here that we haven't actually found the local minimum. We just know the location of it. So it might be a good idea to go ahead and find what that local minimum value is. Now remember, the local minimum is actually the y value at this particular x value. And so to do that, you just have to go back and plug -1 into the function to find the corresponding y value. Okay, so let's go ahead and do that. So let's plug this into the function, plug -1 into the original function to find the corresponding y value. Okay, so here you get 3. -1 cubed is -1, but then when you multiply by the -4, you get a +4. And then -1 squared is 1, so this becomes -6. This is -12, and then +1. Okay, so it looks like we get 7 minus 6 is 1, minus 12 is -11, plus 1 is -10. Okay, so this is actually the local minimum. All right, we have a local minimum of -12, and it happens to occur when x is -1, and that's the only local minimum or local maximum that we have. Now, let me go ahead and show you the graph of this, just so you can see visually what's happening. Okay, so the graph of the function looks like this. And you can see at -1, right, when x is -1, you do have a local minimum of -10. But then at x equals 1, you have neither a local max nor a local minimum. And you can see that the first derivative test actually works. It was decreasing on this side and then increasing on this side, and that's how we knew we had a local minimum at -1. But then at 1, that critical point, it continued to increase. You know, it was increasing on the left of it and then increasing on the right of it. And that indicates that it's neither. Okay, so that's how the first derivative test works. Using the first derivative test, we're able to classify all the critical points for the function as either being the location of a local maximum, a local minimum, or neither. Okay, I hope you found this video helpful. Thank you for watching. Bye-bye.